I'll take down another one real quick here, but I like Parth.
Hey
I
everyone,
like the
Parth
other guy
here,
too.
and
He
in
actually
this
did
video
good
I
one,
want
but
to take a look at an equation used in the study of electromagnetism that is known as the Lorentz force equation. We'll be understanding what each of the terms in this equation means, but as always we'll try and keep the mathematics as simple as possible. So if you enjoyed this video, then please do hit the thumbs up button and subscribe for more fun physics content. Let's get into it. The first thing we should understand is that the Lorentz force equation deals with the force exerted on a charged particle by electric and magnetic fields. So let's take a look at these fields. Electric fields, firstly, can be used to describe how electric charges interact with each other. The convention that we most often use in physics is that electric field lines begin at positive charges and they end at negative charges. These field lines essentially represent the force that a small positively charged particle would experience if we were to place it in the electric field. And this sort of makes sense, like charges repel, so the small positive charge will be repelled from the large positive one, and opposite charges attract, so the small positive charge will be attracted to the negative charge.
Yay.
But these electric field lines give us a little bit more detail about exactly how this small positive charge would interact with the electric field. It's also worth noting here that electric fields are vector fields. This means that we can assign a vector to every single point in this region of space. The size of each vector is related to how strong a force our small positive charge would experience, and the direction simply gives the direction in which the force is applied.
You want
Now,
to be a
similar to electric
mathematician
fields, we can
or
also think
something
about
else?
magnetic fields. Our chosen convention is that magnetic field lines emanate from the north pole of a magnet, and they are absorbed into the south pole. Magnetic field lines are a little bit more complicated than electric field lines in that there can also be magnetic field lines inside our magnet. Check out this video I made a while ago explaining this in more detail. But for now, if we just think about what's
Competitive
happening
equilibrium of
outside the magnet,
monopolist.
then our magnetic
Sounds
field
about
lines
right.
for this particular bar magnet look like this. They essentially begin at the North Pole
You
and
can be a
end at the South
mathematician
Pole. The reason
or
for this is that magnetic field lines represent what would happen to a small North Pole if placed in the magnetic field. Like poles repel, so it would be repelled away from the North Pole of the bar magnet, and opposite poles attract, so it would be attracted to the South Pole. Now, in reality, single poles, either north or south, do not seem to be able to exist in our universe. It seems like both North and South Pole must exist together. So another way to interpret these magnetic field lines is to imagine that they're representing the direction in which a small compass will point when placed at that point in the magnetic field. For example, if we place the compass here in the magnetic field, its needle would spin, so it's pointing in this direction, and similarly for this point in space, this point in space, and this point in space.
You're all
Now,
done.
magnetic
Between
fields are
us,
also a type of
this is gonna
vector
rip
field
you
in that
apart.
we can assign a vector to every point in this region of space. And this is similar to what we saw for electric fields earlier, except the things generating electric and magnetic fields are different, at least on the surface. Now, with that brief overview of both the electric and magnetic vector fields, let's return to our Lorentz force equation. We might at this point be able to recognize a couple of terms in it. For example, we can see the electric field represented by E
Lorentz
and the
force
magnetic
equation.
field represented by
Blossoming
B.
sands.
And because they're both vector fields, we're representing them with
Electric
vectors,
field,
hence the arrows on
and I
top.
got storm
Now, as we
cauldron
mentioned
and
earlier,
shift
this Lorentz
stitches
force
graph.
equation allows us to calculate
Electric
the
field
force
and
that a small charged particle will experience when placed in an electric and magnetic field. In this case, the particle will have a charge Q. That's what this Q is representing in the equation. And a useful thing to do here is to expand the bracket
Q.
by multiplying each of the terms by Q.
Ah.
Now what we've got are two separate terms. F is equal to QE plus QV cross B.
Carl Sagan
What we're
universe
seeing
loaf.
here is simply a
You want
sum
to
of
be
two different
something
forces.
that's not a mathematician?
This is the
Stone
force
mill.
exerted by the
This
electric
dude's
field
house.
on our small
It's
charged
like
particle,
knowing
and
the
this is the
volume
force
of the
exerted
crown
by the magnetic field
by
on
just
our small
doing
charged
air
particle.
turbulence
We'll see
equations
what V
in your
means very
house.
shortly,
Now, we
as
can
well
X
as
that
why we
off
write
and
what looks
make
like
it a box, a
multiplication
board
symbol
cube,
between two vectors.
if we wanted to.
But before we do that, let's take a look at
Before
the
we do that.
first part of this equation, the force exerted by the electric field QE. This is the
Something Carl
easier of the
Sagan
two terms to
universe
think
loaf,
about,
like I said.
because if we have a
What you're looking
particle
at
with
is
charge
this
Q
equation,
placed in an
Lorentz
electric
force
field,
equation,
the
Lorentz
force that this particle
transformation,
experiences
Feynman's
is
how to
Q
learn
times the
anything
strength of the
technique.
electric field E. And we also
And
go one
I'm gonna
step
generate
further by
energy
making
off
this
this.
a
You're gonna be
vector
like,
equation,
no,
which
you're
means that the
crazy, and I'm gonna be
direction
like,
of the force
supreme
exerted is
birdie.
also included. This is done because we're keeping the vector version of the electric field E rather than just thinking about its magnitude or size. And so the stronger the field, the stronger the force our charged particle experiences, and the direction of the force is in the
It's a
same
sunny day
direction
out
as
here.
the
It's
field
nice.
lines.
It's good.
So that's the electric force exerted on our charged
You
Q.
come out there.
Now let's think about the magnetic force, which is slightly trickier. It turns out that if a charged particle is placed in a magnetic field, and that charged particle is stationary relative to the magnetic field, then the
Pendro.
magnetic field doesn't
Now,
actually
Pendro
exert a
doesn't change
force on the
universes,
particle.
but it'll
However,
change the number,
if the charged particle is
FMA,
moving
if an object
relative
is
to the
moving with a
magnetic field,
constant
then
force.
it can experience a force. This is where our vector v comes into
And
play.
the field would slow it
This
down,
represents
or
the
give it
velocity
spin.
of our charged particle.
Okay.
And it's a vector because velocity itself is a vector. It's got magnitude,
And
or
then he's going to
size,
talk about
which is
spin
the
of a
speed of the
particle between the distance
and
of
it
this
also
one and
has
this one over
direction,
here.
which is
And
the
then
direction in which the
some
particle is
quantum
traveling.
function of
The magnetic
hydrogen.
field exerts a force on our charged particle that is equal to
This is
q,
fission.
the charge of the particle, multiplied by v
Well, then you get into
cross
some
v.
Pendro stuff.
Now let's take a look at what this last bit actually means. V is the velocity of our particle, which is a
saying
vector.
this is the measurement
B
tool.
is the
The
magnetic
particle
field, which is
is
also
that
a vector.
determines the
And
time
what we're
on that
finding
test.
here
If you
is the
can't figure out
vector
that test
product
because
or
it is
cross
physics,
product
if
between
I
these
shoot it
two.
out of a
It's not just a
baseball
simple
cannon,
multiplication like there is between two numbers, say. For those of
but
you
this is
unfamiliar
different.
with vector
You know,
products, this
this
how
is
they
top
work.
and spin
If we take
collision
two
to make
random
new.
vectors, let's say A and B,
We're
let's
gonna
not say they
we're gonna
represent
remake
anything
new.
particular, they're just mathematical entities, they're just vectors. And we want to try and find the vector
Make as many
product, A
collisions
cross
in you
B,
as possible.
between these two vectors. Then the end result is going to be another vector that is perpendicular to both
We're gonna get
A
that
and
working.
B,
We're
and
gonna get
whose
that not
size
working.
and direction
And we're gonna find a bunch
depends
of
on
other
how
things that
well
work.
A and B are aligned
And that's
with
this.
each other.
It
Now,
works,
as it turns
just
out,
not
if A
the way I
and B
wanted Hubble
are exactly
45.
perpendicular to each other at 90
turn this,
degrees to each
invert
other,
it.
then the vector product A cross B, again, will also be perpendicular to the original
there.
two, but its size will be as large as possible. Its size will be equal to the size of A multiplied by the size of B.
Yeah, see,
However,
he yelled at
if
me.
these two original vectors A and B are exactly aligned with each other, or exactly anti-aligned,
Can't add stuff.
then the
You
size
can't
of
do
our
stuff.
vector product A cross B is going to be 0. So now let's link all of this back to our magnetic field and the charged particle placed in this field. Let's
How you doing
imagine
so
that our
far?
magnetic field lines are pointing in this direction. What this is representing is magnetic field lines coming out of the screen. And let's also imagine that our charged particle is initially moving in this direction. So that is its velocity vector. Well, because the magnetic field lines are coming out of the screen in this scenario, this means that V and B are perpendicular to each other. And the end result, V cross B, is going to be another vector that is perpendicular to them both. So our V cross B vector looks something like this. Now, if we take this vector and multiply it by q, the charge of the particle,
there we go.
which essentially just resizes the vector because charge is just a scalar, then what we get is the force exerted on this particle by the magnetic field. And as we can see, the force exerted is directly perpendicular to the initial velocity of our particle. As we expected, right? A cross product is always going to be
YF over X.
perpendicular to one of the original
See?
vectors. Which means that our particle, instead of just
Yeah, you
moving
do
straight
stuff,
across,
but
is
it'll
going
be
to
a
be
Y.
pulled
You can make
slightly
the
in this
geometry,
direction
it's like
due
a
to the
light.
force. But
Turn
then,
it
at
and
some
do
later
stuff
point
with
in
it.
time, it's now going to be moving in this direction. And if we
Take
repeat
saw,
the process by
make
working
Stanford.
out V cross
Take
B,
piece of artillery.
and then
Oh
multiplying
yeah,
that by q,
definitely Stanford.
then we find that the force exerted by the magnetic field
Winter
now
in
points
Russia.
in this
Atomsot,
direction.
the
And we
new
can repeat
statue
this
of
process a
David.
few times, and what we see is that our particle will move along a circular path. This is circular motion, and for those of you
Gravity.
familiar with
We've
it, the
been doing
force
it
is
in
always
this form
perpendicular to the direction
on a very
of the
specific
velocity
timeline,
of
which
any
is
object
tested
moving in a
by
circle.
MCATs
This
and brain
means that
scan
the
of that
speed
room.
of
Some
the
drill
object
sergeant
doesn't actually
hammering your
change
ass,
unless
just
there are
floating
some
around
other
this
forces
motherfucker
being
like a
exerted on
goddamn
the
pursuit
particle.
algorithm.
But in this scenario, that's not going to happen because we've just got a magnetic field and a charged particle.
This is a real
But
one.
interestingly, the
It's a good
direction
one.
of
It's a
motion
good one.
changes constantly. It moves in a circle. And so what we see here is that the force exerted by a magnetic field on a moving charged particle causes it to move along a circular path. But the most essential point that we've seen here is that a magnetic field can exert a force in the first place
G.
on a charged
Or Q.
particle. And that force is given by QV cross B. At which point we can return to our Lorentz force equation. We can see now that if our particle is placed in a region of space where there's both an electric field and a magnetic field, then the total
You
or
are
net
here
force on a
right now.
particle is going to be given by this equation. This is the
He's
contribution
talking
of
math.
the
I'm
electric
telling you
field,
to just do
and
the
this is the
stone belt. First
contribution of
page
the
is F
magnetic field.
equals
And so that
change.
is an overview of what each term in the Lorentz force equation represents
Now,
and how we
he's
can
going to
use
do that
it.
very
And with all of that being
differently
said, I'm going to finish
over
up
where
here.
they need
Thank
to
you
do
so
it
much for
like that.
watching.
Very
If you enjoyed
differently.
the video, please do hit the thumbs up button and subscribe for more fun physics content.
That was fun.
Hit that bell button if you'd like to be notified when I upload.